Welcome back to the deep dive. Today, our mission, should you choose to accept it, is getting into the nitty-gritty materials science behind modern pipelines. The ones running across continents, under oceans.
Yeah, these things are serious business. They move vast amounts of, product over huge distances and often in really tough spots. Think deep sea, freezing Arctic conditions, shaky ground.
So steel is the go-to material, right? We see these API grades mentioned like X65, X70, X80.
Exactly. Those are the standards. Steel's the workhorse.
Just quickly, for folks who know the area but maybe aren't metallurgists, the X and the number, what's the basic idea?
Good question. The X just marks the grade, and the number, that's the minimum yield strength, usually in case I, or thousands of pounds per square inch. So X80 is quite a bit stronger than, say, X65.
And the industry's really pushing towards these higher strengths. X80 seems pretty established now.
Oh, yeah. X80 is definitely in service, you call it. Flight proven is a term one source used.
Flight proven. That sounds like aerospace talk.
Yeah.
Are they borrowing safety ideas, or is it just industry jargon for it works reliably?
It's a bit of both, I think. It signals that the whole process, the alloying, the specific thermomechanical treatment to get those X80 properties, it's dependable, been used successfully on major projects.
Makes sense. And the payoff is higher pressure transport, or maybe using less steel, thinner walls.
That's the idea. Higher pressure or reduced weight. Big potential savings, big efficiency boost. But, and it's a big but, despite this strength, there's this stubborn technical problem.
Which is what we're really diving into today. Anisotropy, specifically the anisotropy of toughness, which just means the material isn't the same in all directions. Its strength, or more importantly, its toughness, its resistance to fracture changes depending on how you load it or test it.
And for something like a pipeline, you absolutely want consistency, uniformity.
Right.
Measuring that toughness usually comes down to the Charpy impact test. It's a standard.
Right, the Charpy test. That gives you that S-shaped curve, doesn't it?
It does. You hit a notched sample with a pendulum, measure the energy it absorbs at different temperatures. That curve shows you everything.
So the top part of the S, the upper shelf, that's where it behaves ductily, absorbs a lot of energy before failing.
Correct. That's the ideal tough behavior. Then there's the bottom part, the lower shelf, where it's brittle, snaps easily with little energy that's cleavage failure.
And the bit in the middle is the transition zone.
Precisely. And anisotropy messes with this whole picture. It means the energy values, both ductile and brittle, depend on the orientation of the test sample relative to how the steel was made.
Which is a nightmare if the direction facing the highest stress happens to be the weakest one.
That's the core risk. So we need to understand why this happens. The source material we looked at highlights three main culprits for this toughness anisotropy in hot-rolled pipeline steels.
Okay, let's break them down. Culprit number one, unwanted guests, the non-metallic inclusions.
Right. These are basically tiny impurities left over from steelmaking things like manganese, sulphides, silicates, aluminum particles. They're always there to some extent.
But the problem isn't just that they exist, it's what happens when you roll the steel plate hot.
Exactly. The hot rolling process involves massive plastic deformation. This squashes and stretches everything, including these inclusions. They tend to get elongated and line up along the rolling direction.
Like tiny weak threads running through the metal?
Sort of, yeah. Take manganese sulfide, MNS. It's relatively soft at rolling temperatures, so it either deforms and gets stretched into long, flat shapes, or it breaks up into lines of fragments. We call them stringers.
Stringers, and these create weak planes.
They do. Think of that like wood grain, easier to split along the grain. Same idea here. The fracture toughness is measurably lower when you test it in a way that the crack can easily follow these stringers.
It's pretty wild that microscopic bits of sulfur residue can compromise a massive pipeline, and the tests confirm this difference in toughness based on orientation.
Absolutely.
Yeah.
It correlates directly with the shape, the aspect ratio, of these MNS inclusions. And here's something interesting, almost counterintuitive from the sources. The sulfur paradox.
A paradox. Go on.
You'd naturally think lower sulfur content is always better for reducing this problem. But one study found a case where a steel with higher sulfur actually showed less anisotropy than a lower sulfur version.
Wait, what? Less sulfur made the directionality worse? How does that work?
It sounds completely backward, I know.
Yeah.
But it really highlights that the shape of the inclusions is the dominant factor, maybe even more than the total amount.
So in the low sulfur steel, the few sulfides that were there got stretched out even more extremely during rolling?
That seems to be the explanation.
Yeah.
They ended up with a higher aspect ratio, flatter, and longer, making them more effective weak planes. So the shape effect overwhelmed the benefit of having fewer of them overall.
Wow. Okay, so shape is king here. That shifts the focus for fixing it. How you control the shape.
Well, the obvious first step is still reducing sulfur overall. You want clean steel. But even below 0.01%, anisotropy can persist.
So cleaning isn't enough on its own.
Not entirely. You can also try reducing the amount of deformation during rolling, which leads to less stretching, smaller aspect ratios. But maybe the cleverest approach is chemical.
Adding something else to the mix.
Exactly. Adding elements like cerium or zirconium or titanium. These react with the sulfur and oxygen. They form compounds that are much harder and less deformable at rolling temperatures.
Ah, so they form little balls instead of pancakes.
Pretty much. They create more spheroidal inclusions that don't elongate easily during rolling. That prevents those weak planes from forming. It's called inclusion shape control.
Okay, that handles the foreign invaders. Let's move to culprit number 2. This isn't about impurities, but the steel's own structure, right? Chemical segregation causing banding.
That's it. Microstructural banding. It goes back to how the steel first solidifies from liquid. As it cools, some elements, manganese is a key one, but also silicon phosphorus, tend to get pushed into the liquid that solidifies last. These are the interdendritic regions.
So even in the solid slab, you have tiny variations in chemistry. Some spots are richer in certain elements than others.
Precisely. Then, just like with the inclusions, when you hot roll this slab, those chemically enriched regions get squashed and smeared out into long bands parallel to the rolling direction.
And manganese is particularly bad for this.
It is, especially if the cooling after rolling is relatively slow.
Yeah.
The manganese-rich bands tend to transform into pearlite, a harder layered microstructure, while the surrounding areas become softer ferrite. This creates distinct ferrite-pearlite bands.
So you get layers of harder and softer material running through the steel. That sounds like another built-in weakness.
It definitely is. It's a major source of microstructural anisotropy. And it can lead to a visible phenomenon during testing called splitting or delamination. You actually see separations opening up parallel to the rolling planes.
Splitting. Okay, but then there's this toughening paradox, as you mentioned. How can splitting be good?
Right, it's complex. Usually at higher temperatures up on the Charpy upper shelf where you want ductile behavior, splitting is bad news. It acts like a premature brittle failure. It lowers the absorbed energy.
Okay, that makes sense. Lower toughness. Bad.
But if the splitting happens at low temperatures, down in the brittle transition range, sometimes it can actually help.
How?
Because the crack, instead of running straight through, gets diverted along these weak banded layers. Each time it splits or delaminates, the separation itself absorbs some fracture energy. It forces the crack to take a more tortuous path.
Ah, so it kind of interrupts the main crack propagation, absorbs extra energy, making those side cracks.
Exactly. It's called delamination toughening. So, the same feature that hurts toughness in the ductile regime can, paradoxically, provide a boost in the brittle regime.
That is fascinatingly complicated. Shows why you need to test across the whole temperature range.
Absolutely. You can't just optimize for one condition.
Okay, inclusions dealt with, banding paradoxically understood. What's the third major factor, especially important for the really high-strength steels like X80? Crystallographic texture.
Texture, yeah. This one's about the crystals themselves. In a perfectly random material, the tiny metal crystals, the grains, would be oriented every which way. But the thermomechanical processing, the rolling and cooling, tends to make them align in preferred directions.
So it's not random anymore.
Not at all. You get a non-random distribution of crystal orientations. That's texture. And it matters because how easily a crystal deforms or fractures depends heavily on its orientation relative to the applied stress.
Can you give an analogy? How does crystal alignment affect strength?
Sure. Think about a deck of cards. If you press down on the flat face, it's strong. But if you try to slide the cards past each other, parallel to the faces, they move easily, right?
Yeah, they shear easily.
Metal crystals have similar easy slip or easy cleavage planes. If the rolling process aligns many crystals so their weak planes are all pointing in roughly the same direction, the steel will be much weaker when stressed along that direction.
Got it. So these codes we see, like 100 or 12, are just ways scientists label these specific crystal planes or alignment directions.
Exactly. They're Miller indices, a way to describe crystallographic planes and directions. For brittle fracture, cleavage, the planes are key. So texture components related to alignment, like 0100001, become really important for low temperature toughness anisotropy.
And for ductile failure at higher temps.
Then it's more about the slip systems, the planes where plastic deformation happens easily. So texture components like 110 might correlate more strongly with upper shelf energy anisotropy.
Does texture become more important as you go to stronger steels, like moving from X65 to X80?
Generally, yes. That seems to be the trend. In older or lower grade steels, the inclusions and the banding are often such big problems that they dominate the anisotropy.
The low-hanging fruit, so to speak.
Right. But as steelmaking gets cleaner and processing more controlled for grades like X80, you reduce the impact of inclusions and banding. Then the underlying crystallographic texture can emerge as the main factor controlling anisotropy. It becomes a limiting weakness.
It's like peeling an onion, solve one layer of problems and reveal another underneath. But I gather the science isn't totally settled on how much texture matters compared to, say, residual banding.
No, there's definitely debate in the literature. Some studies, particularly looking at the brittle transition in X80, find strong links between texture and toughness variation. Others argue that even in clean steels, subtle microstructural variations, like very fine banding, might still be playing a bigger role than texture.
So it's complicated, the interaction between all three.
It's essentially complex, as one source put it. Inclusions, banding, texture, they're all created or modified by the same rolling process, so they're often linked. Teasing out the exact contribution of each is really challenging.
Okay, let's pull this together. We have these three interconnected causes of anisotropy. What's the big real-world consequence, especially thinking about those huge spiral-welded pipes used for transport?
The major issue is how the load lines up with these weaknesses. In a large pipeline under pressure, the biggest stress is usually circumferential, the hoop stress trying to burst the pipe open.
Right, the stress acting around the circle of the pipe.
Yes. Now, because of how spiral-welded pipes are made, winding a rolled steel plate into a spiral, welding the edges, that critical circumferential direction often aligns with the direction on the original plate that has the lowest toughness and strength due to anisotropy.
Oh, wow. So the direction experiencing the maximum load is potentially the weakest direction in the material itself?
Precisely. That's the design nightmare. You're putting the highest demand right on the material's weakest point. It significantly increases the risk of fracture initiation.
So all that effort to get high-strength X80 steel could be undermined if the toughness in that critical hoop direction isn't good enough because of these inherent anisotropy issues.
That's the fundamental challenge. The very process of making the strong plate introduces directional weaknesses that line up perfectly with the service stresses in some common pipe designs. We've seen why that toughness isn't uniform. It's down to these three culprits: inclusions, banding, and texture.
It really highlights this constant balancing act in material science, pushing for higher performance, like strength, but always battling these more subtle, inherent limitations, like anisotropy.
It does, and that leads perfectly into a final thought, something provocative for you to consider based on what we've discussed.
Lay it on us.
Okay, so we noted that reducing carbon helps reduce perlite banding, making the steel potentially more isotropic, right? And modern high-strength steels generally have lower carbon contents anyway. So the question is, as metallurgists push for even stronger grades, think beyond X80 towards X100 or even higher, how much further can they go before the benefits of that raw strength are completely negated by the persistence of anisotropy? Will we hit a wall where increasing strength just doesn't help anymore because the directional weakness, maybe dominated by texture at that point, becomes the unavoidable failure mode?
A point of diminishing returns where the quest for strength is beaten by the lack of uniformity. That's a heavy question.
It is. It defines the cutting edge of pipeline material development.
Well, that's definitely food for thought. Thank you for breaking down this complex science with us today. Hopefully this deep dive gives you, our listener, a new appreciation for the incredible materials engineering hidden inside the infrastructure we rely on every day. Keep digging, keep learning.